Welcome to the second video on volumes of revolution by Washer method. In this video, we're going to go beyond just volumes that go around the x and y axis. The good news is the formula is exactly the same. So let's just review that formula. We had pi, the integral from a to b, our big radius squared minus our small radius squared times dh, where h is that width of my washer. You have this in your homework handout, and we're going to fill this out right now to look at the different cases. But really, I want you to see all three of these as the same case. But we have a horizontal line that we're revolving around this region around it. We have a horizontal line below the region that we're going to revolve it around. And we also have one below it that's also below the x-axis. This may seem like I have three separate cases, but they're really all treated the exact same way. And we have to just remember that a vertical distance is calculated by finding the top function minus the bottom function. All right, so let's start with this first one. We're going to take this region, we're going to revolve it around y equals 3, and when we do so, to draw a radius, we're going to start at that axis of revolution and come down to the function farthest away to find our big radius. To do that, remember I talked about top minus bottom. My top function is 3, my bottom function is g of x. So 3 minus g of x gives me the length of this blue big R. Now I'm going to find little r, and little r is the distance from here down to the first function I hit, and that is going to be top function minus bottom. This time it is 3 minus f of x. Once we've found our big R and little r, then writing our integral is quite simple. We have pi out front. We can see that our washers, or radiuses even, are going to go from a to b. We take our big radius, 3 minus g of x, put it in parentheses, squared, minus our little radius, 3 minus f of x, in parentheses, squared. All of that times dx, because the width of our washers is horizontal. You can even think of this little line, the width of the line being a horizontal dx. All right, let's try our next one. Down here, we are revolving around y equals 1. So we're going to go from that up to here for my big one. And that is r equals, this time my top function is f of x. So I'm going to just do f of x minus, and because this function is 1, it'll be 1. I'm going to draw my little r here. Be consistent with color, actually. There we go. Now it's red. Little r equals, the top of that function right there is g of x minus 1, where the dashed line is. And now I'm ready to write that integral. So I've got pi, the integral. Again, these are stacked from a to b. Big radius, f of x minus 1 squared, minus little radius, g of x minus 1 squared, and all of that times dx. All right, we've got one more here. We'll start off with our big radius, and we're going from -2 all the way up to there. So my big R, now you might think I have to do something different, but I don't. I'm going to take f of x minus -2. And we'll see that's going to turn to a positive, but I'm still simply just taking the top function minus the bottom function. And for my little r, I go from here all the way up to there, and little r equals top function g of x minus -2. And so when I'm ready to write the integral, I've got pi. These also are going from a to b, and I've got my big radius. I'm going to simplify that, f of x plus 2, all of that squared, minus my little radius, g of x plus 2, all of that squared, and the whole thing times dx. All right, so now we've got three more of these, but this time look what we're revolving around. We're revolving around vertical lines. And for these, we're going to be finding a horizontal distance. And to figure out our horizontal distance, instead of top minus bottom, it's right minus left. Right minus left because the big numbers are on the right and the small numbers are on the left. So let's do the same thing. And we start from this line and go out here, and there's my big R. And big R is going to be, my right function is here at 6. 6 minus, and this function is f of y. My small radius goes from here to here to the red one, so little r equals 6 minus g of y. We can see that these are going to have a thickness of delta y, and they're going to be stacked from c to d. So my integral, pi, integral from c to d, my big R, 6 minus f of y, all of that squared, minus 6 minus g of y, all of that squared, times dy. All right, we got 2 more to go. We'll probably get through these a lot quicker. So again, from the dashed line out here, there's my big R, and big R equals my right function, which is g of y, minus the left one, which is at 1. My little radius right there is little r, and that's going to be my right function, f of y, minus 1. And so my integral is pi, the integral from c to d, big R, g of y, minus 1 squared, minus f of y, minus 1 squared, the whole thing, times by. All right, one last one. Right here, we're going to be drawing our radius all the way from -3 all the way out to here. Big R equals, my right function is g of y minus -3, and my little r goes like this. Little r equals f of y minus -3. We go to write our integral, pi. They get stacked up from c to d. My big radius simplifies to g of y plus 3 squared, minus my little radius, f of y plus 3 squared, the whole thing, times dy. All right, so let's use this to actually do a problem like you might see in your homework. So we've seen this region before. It is bound by x cubed, x equals 0, and x equals 8. I'll just color it in for us here. So here's our region, and we are asked to write and evaluate, and in this video we're just going to write. So we're not actually going to find the answer. So we're going to write the integral for the solid form if the region is rotated around the line y equals 10. So here it is, our line y equals 10. All right, so like I do with all of them, I'm going to draw my radius starting from that line going down to the function. There's my big R. And my big R is going to be 10 is my top function minus the bottom one is this curve, and that curve is x cubed. So 10 minus x cubed. My small radius, I'm going to draw from here, and r equals, well, that's just 10 minus 8, because remember this is at a height of 8. 10 minus 8, or just 2. So when I go to write this integral, I've got pi. Notice that these have a width of delta x, which means I'm going to use x values. So they're going to go from 0 to 2. And my big radius, we said, was 10 minus x cubed squared. My small radius is just 2 squared, and all of that times dx. Let's try another one. All of these we're just going to write the integral. And this time we're going to go around the line x equals -1. So here we go. Here's our line, x equals -1. And if we just shade this in real quick again so that it's clear to see what we're doing. And so we'll start with our big radius. So our big radius goes from this line all the way out here. Now we should right away recognize, wait, this has a width of delta y. And so I'm going to have to rewrite this equation so it's x equals the cube root of y. All right, so when I do that, I'm going to take right minus left. So big R, my right function is this one, and it is the cube root of y. And I'm going to subtract my left function, which is at -1. So cube root of y minus -1. For my small radius, right here, well, I can see that's simply the distance between 0 and -1. Clearly, that's simply 1. But I could have done 0 minus -1, and that's 1. You'll see that right minus left still works. Now, anytime you want to use what's obvious and just say, well, clearly that radius is always 1, you can do that. So now we're ready to write our integral. So when we write our integral, pi, you should notice that as I draw these radiuses, they're stacked up. And so they're going to start all the way down here from 0 and go all the way up to 8. So 0 to 8, my big radius, cube root of y plus 1 squared minus 1 squared, all of that times dy. All right, let's try another one. This time, same region. We'll just get that colored in again. So same region. And this time we're going around the line x equals 4. So 1, 2, 3, 4. Here it is. We're at x equals 4 is what we're revolving around. So let's start with our big radius. We're going to start from that dashed line, go all the way there, and I can see, oh, that big radius is always going to be 4. Now for my small radius, I go from here over to here. And again, I should recognize, oh yeah, these have a thickness of delta y. And so I'm going to need this equation in terms of y again. So x equals cube root of y. And when I do, for my small radius, right minus left, my right function is 4 minus the left function, this one, cube root of y. So then I'm ready to write my integral. Pi. I should see that these horizontal lines I've been drawing are going to get stacked up from 0 to 8. My big radius is 4, square that, minus my small radius, 4 minus cube root of y, square that, all of it times dy. All right, we've got one last example we're going to do. We've got this region. It looks a little different than our other regions, but the region we're looking at here is inside of this. And it is bound by these two equations. You can see the first one is a parabola, so that's got to be the curve. The second one is a line. And we're supposed to revolve it around the line y equals -1. So here it is, y equals -1. So same as before, I'm going to draw my big radius. I start here and go up to the top. And for that big R, I'll write it over here, big R, I'm going to take top minus bottom. We said our top function is x plus 1 minus -1. And I can always simplify this. This looks like it'll be x plus 2. My little r, I'll switch colors. So let's go. So for my little r, I'm going to go from here up to this function right there. Actually, I'm going to draw that a little further over so we can clearly see that it goes up to that function. So my little r, let me draw one over here, goes up to here. There's little r. And again, top function, x minus 1 squared minus -1. Or I can write it as x minus 1 squared plus 1. So now we're ready to write our integral. We should have noticed that these have a thickness of delta x, which means I'm going to be taking them from the leftmost point, x of 0, all the way over here, and this one is at 4. And in this case, I was able to read it right off the graph. And so I've got pi, the integral from 0 to 4. My big radius is x plus 2 squared minus my small radius, which is x minus 1 squared plus 1, all of that squared, put parenthesis around all of that, dx. All right, there you go. Good luck on your homework.